Hello, chemists. This is Ms. Placino, and you're watching lesson 9.1 on specific heat and phase changes. In today's lesson, we're going to talk about how changes in energy are measured. We're going to be doing a lot of calculations during this lesson, so you probably want to have a calculator handy, and it wouldn't hurt to have your reference table nearby as well. Goals for today's lesson. You should be able to define what specific heat is. We'll take care of that right off the bat. Big one for today has to do with applying and solving different heat equations. There are a total of 3 of them. And finally, we're going to interpret the heating curve. This kind of came up in lesson 7.3 and apply the heat equations to calculate heat lost or gained. So really just an application of those heat equations. Let's get started. All right, specific heat capacity, sometimes just called specific heat. And when we see it in formulas, it's going to be a capital C. Don't confuse it with degrees Celsius. Specific heat capacity is the amount of heat per unit mass, so usually the amount of energy measured in something like joules per unit mass, often measured in something like grams for our purposes, required to raise the temperature of that substance by 1 degree Celsius. Materials can have a high specific heat value or a low specific heat value. I know those are 2 very relative terms. We'll be putting some numbers to it later this lesson. Something that has a high specific heat is going to retain heat well. It's also going to heat up and cool off slowly. Materials with low specific heats are conductors of heats. So they're able to heat up and cool off quickly and really transfer that energy to another substance. We see examples of high and low specific heat materials all the time. You've probably experienced this in the kitchen. If you go to boil water on the stove, it's going to take a while for that water to warm up. But once it's hot, it also takes a long time for that water to cool down. Water has a high specific heat. If you think about the pots and pans in your kitchen, they're going to heat up and cool off pretty quickly. Like if you're baking cookies or something, you're going to put the tin in the oven. It's going to transfer the heat from the oven to the cookies. And you know that once you take that cooking tray out of the oven, it cools off fairly quickly. We can also look at specific heat kind of in terms of molecular movement. Here we've got a particle diagram. We're going to apply heat. Now, we know that as heat is applied, we're going to see molecules or particles moving faster. But when we're talking about something with a high specific heat that is going to heat up and cool off slowly, we're going to get some more movement, but nothing too crazy. Low specific heat, which is going to heat up and cool off quickly, will be much more impacted, and you'll see a bigger temperature change because the molecules are moving at a faster speed. So we're going to kind of come back to this concept throughout this lesson, and we'll start putting some numbers to specific heat capacity. Before we do that, I want to show you this quick video about balloons and specific heat. So in each of these red balloons, the first one is filled with water. The one that's kind of behind it has been blown up, so just kind of filled up with air or carbon dioxide. And we're going to put both of them over that candle flame. Now you know that a balloon is made out of like a latex rubber sort of material, and it can melt. So just kind of make a quick prediction in your head about what might happen when we put each of those balloons over the flame. Let's see how this turns out. So we're taking the water-filled balloon first. We're putting it over the flame. It's actually touching the flame. And it doesn't look like much of anything is happening. We've got a little bit of char, like kind of on the bottom of the balloon. Let's repeat that with the one that's filled with carbon dioxide. Oh, and very quickly it pops and deflates. Why was the water balloon able to be touching the fire and not have really any impact whatsoever, where the carbon dioxide filled balloon, after a very short period of time, burst? This has to do with specific heats. So with the balloons, we've got one filled with carbon dioxide. We've got the other filled with water. These 2 substances have 2 dramatically different specific heats. Carbon dioxide, it's about 0.82-ish joules per gram degree Celsius, where water is roughly 5 times that amount at 4.18 joules per gram degree Celsius. When we put fire That's what that's supposed to be. I know, not the greatest art ever. Underneath the balloon, what is happening is the heat is being transferred through the balloon, and it's going to be absorbed by the substance the balloon is filled with. So liquid water is able to absorb a lot of heat. So as the flame is in contact with the balloon, the heat energy is just being transferred to the water. The water is absorbing that energy, and we're seeing virtually no change in temperature. On the other hand, with carbon dioxide, that same process. The flame is in contact with the balloon. The balloon, or the material, the kind of rubber latexy stuff, is transferring heat to the carbon dioxide molecules. They're not able to absorb all of that heat. So we're going to see a big change in temperature, which will be great enough to kind of melt the balloon, causing it to pop and deflate. So it's these two differences in specific heat that give us dramatically different behaviors with the two balloons. So let's talk a little bit more about heat. When we're talking about heat, we're talking about the form of kinetic energy that flows from one object to another due to differences in temperature. Kinetic energy is the energy of motion or movement. So heat is the flow of this energy, and that can be kind of tough to visualize. So I want to show you another quick video. Over here on the right side, we've got a flame. And then over on the left side, we have your hand. And we're taking a glass rod and we're putting it in the flame. Glass, not a great conductor of heat, but we've got something in the solid phase. So we've got all of our particles and pretty well organized. And as we put this glass rod into the flame, what's going to start happening to the speed of the particles that are closest to the flame? Up here, you're thinking, well, they're going to experience an increase in temperature, which means they're going to move faster. As they start to move faster and they start to collide with neighboring molecules, what's going to happen to those neighboring molecules? Well, they should experience an increase in kinetic energy as well. They're getting hit by a faster moving particle, so some of that energy is going to be transferred to them. Let's watch that play out. So everything's kind of vibrating in place in the solid phase. The particles that are closest to the flame have turned red, meaning they're moving faster, and they're colliding into neighboring molecules. We can kind of see that transfer of energy just happening kind of molecule by molecule, moving from right to left until eventually it gets to the side that you're holding, and then you feel potentially a burn or at least an increase in temperature. That's what heat is. It's that movement or flow of kinetic energy from a hot substance to a cooler substance or a cold substance. And we will always see energy, should be more specific, kinetic energy moving from hot to cold. We use different units for heat, depending on what we're trying to evaluate. A really common misconception is that heat and temperature are effectively the same thing. They are not. Heat is the flow of kinetic energy from basically hot to cold, and temperature is a measure of the average kinetic energy. I know that's a subtle difference. A better way to think of it, or maybe an easier way to think of it, would be to talk about units. Temperature, we're always looking at degrees Celsius or potentially Kelvin. Chemistry class, we're not going to see Fahrenheit. When we try to use units of measurement for heat, we're either going to be using the joule or the kilojoule, which is just the international unit of heat and other forms of energy. We'll be using this one quite frequently. We also have calories and kilocalories, the amount of energy needed to raise 1 gram of water by 1 degree Celsius. You might be saying, hey, I know that word. I see that on food labels all the time. A chemistry calorie, if you will, is the amount of energy needed to raise 1 gram of water by 1 degree Celsius. What you see on your food labels are kilocalories. So either capital C, I know it's a little misleading because that is capitalized. I would be more prone to write it like that just to avoid any ambiguity. But that's talking about the amount of energy needed to raise 1 kilogram of water by 1 degree Celsius. So you're recommended a 2,000 calorie diet. It's 2,000 kilocalories. 2,000 chemistry calories is not enough food to sustain you. You should be able to convert back and forth between joules and calories. So here's the conversion factor that we're going to use. If you look in your workbook, you're going to see a handful of practice problems asking you to make that conversion. Definitely take the time to practice. All right, let's get into a heat equation. So the formula that we're going to be using most frequently for problem solving is this: Q equals mc delta T, sometimes called Q equals mcat. If you take a look at table T in your reference table, the one with all the formulas, towards the bottom, you've got that block of equations that says heat, and it's gone through and defined what all of these variables mean. Heat is Q, and we're going to be measuring it more often than not in joules. M stands for mass. We're going to be using the unit gram. C is our specific heat capacity, joules per gram degree Celsius. And finally, delta T is talking about the change in temperature. We can work in Celsius or Kelvin, and when we go to calculate delta T, I really need you to show your formula for this one, but we take the final temperature and then we subtract the initial temperature. Why is it okay to work in Celsius or Kelvin? If we think back to like the gas laws unit, you had to work in Kelvin, it was essential, but here you can work in either. Any ideas why? Well, you're looking at change in temperature, and it turns out that a Celsius degree and a unit Kelvin are the same. If we think about, to get into Kelvin temperature, we just take 273 and add it to the Celsius temperature. So when we're looking at changes in temperature, regardless of which of those two units you use, the change in temperature will be the same. So don't worry about converting, just be consistent. Of course, if you're going to find change in temperature, you should either have final and initial in Celsius or final and initial in Kelvin. Let's try to apply this formula. Let's take a look at practice problem number 2. So a 25.4 gram sample of copper is heated from 12.8 degrees Celsius to 36.1 degrees Celsius. How much heat was gained? Now we're told the specific heat of copper. This is going to be an application of Q equals mc delta T. I'm asked for how much heat was gained, so I'm going to solve for Q. And I can start plugging in for my variables. My mass, 25.4 grams. C, the specific heats. 0.385 joules over grams times degrees Celsius. And my temperature is going to be the final temperature, 63.1 degrees Celsius minus 12.8 degrees Celsius. Okay. If when you're showing your work, you prefer to just kind of take this delta T term and do the math before showing your work, that's completely fine. So I'm going to simplify it down, just kind of really show my entire thought process. You might be wondering, why is she writing a specific heat term like that? I'll show you in a minute. Okay. Hopefully now it's just a math problem. We can take 25.4 times 0.385 times 50.3, and we should be able to calculate how much heat was gained. We know heat's being gained because we're seeing an increase in temperature. I'm not going to be too picky about sig figs this unit, just be reasonable. More often than not, at this point in time, 3 sig figs kind of fits the bill. You should calculate about 474. Units start to get tricky just because there's a bunch of different ones that you're going to be introduced to and you have to kind of remember. Instead of trying to memorize what units go with which variable, if you substitute in with your units, you can cancel them out and figure out what the unit should be. So for example, I've got grams in the numerator, grams in the denominator. I can cancel those out. Degrees Celsius in the numerator, degrees Celsius in the denominator. I can cancel those out as well. This leaves me with an answer in joules. And sure enough, the unit for energy, or for heat in this case, is going to be joules. So you can always get your units to cancel so that you can figure out what unit should be applied instead of trying to memorize what unit goes with which variable. All right, let's go back and wrap up the notes. So I'd like to apply what we're kind of talking about with heat and phase changes to a heating curve. So we've seen this before, back when we were talking about phase changes in Unit 7. We know that the diagonal lines represent different phases, solid, liquid, and gas, as we go from left to right. And we know that line segments B, C, and DE, the two like zero slope or flat parts of the graph, are representing phase changes. So we've got the change from solid to liquid. We're going to call that fusion. And I know that that can sometimes cause a little bit of confusion. We're not talking about the nuclear chain fusion. We're just talking about the process of melting. So just kind of make a mental note of that. And DE, we're going to see another phase change. We'll call it vaporization. Yes, technically you can use boiling or evaporation. It's the same general idea, going from liquid to gas. When we're in a phase, we can use Q equals mc delta T. We can get the mass, no problem. We can look up the specific heat of whatever substance we're looking at, and then change in temperature. Yeah, we definitely have changes in temperature along line segments A, B, C, D, and DE. So if we're in a single phase, we're able to use the formula Q equals mc delta T. Can I use that formula when I'm talking about either melting or vaporization, or fusion and vaporization? Well, probably not. Think about it. You can't calculate a delta T. By definition, at the melting point and the vaporization temperature, you don't see a change in temperature. It remains constant. So if I plugged in, 0 here, of course that's going to make energy added, in this case Q, equal to 0. And that is not what's going on. You can kind of see that we have increases in energy, so that doesn't really make any sense. So we're going to have to use two different formulas. We've got the heat of fusion, where we're going to take mass times H sub F, and the heat of vaporization, mass times H sub V. If you take a look back at table T with the equations, you'll see that these two are provided as well, and you've got definitions for what H sub F and H sub V mean. What I'd like you to do is flip over your reference table and take a look at table B. Table B is another forgotten table in the reference table. You have physical constants for water. You've got values for the heat of fusion, which is 334 joules per gram, and for the heat of vaporization, which is 2260 joules per gram. And again, this is for water only. This does not apply to every single substance out there. It's just water. So this is a hopefully pretty easy formula to apply. To find the amount of heat required to melt in this case water, at its freezing point or melting point, depending on which way you're approaching it, I would just take the mass of my sample times 334 joules per gram. If I wanted to find out how much energy it would require to vaporize water at its boiling point, kind of the same idea. I'd take the mass of my sample and I'd multiply it by 2,260 joules per gram. So there's a practice problem in your workbook. I think it's number 8, where it actually has you performing a whole bunch of calculations, trying to use these formulas to figure out how much energy is going to be gained by a sample of water as it goes from ice up to gas. So definitely worth trying that question out to see if you can apply these different formulas. All right, I think we'll wrap it up there for today. Thank you for tuning in, and I hope you found this helpful.